There's a current moving beneath the Atlantic Ocean right now. You can't see it, you can't feel it. There is no instrument you own that could detect it. But every piece of weather you have ever experienced in your life, every winter, every summer, every storm that flooded a city, every drought that killed a harvest, has been shaped by it. It has been running without interruption for at least 12,000 years, possibly longer. It ran while the Roman Empire rose and fell. It ran while humans crossed into the Americas. It ran while every civilization in recorded history built itself up, and in many cases destroyed itself. It is not a river, it is not a tide, it is something far larger, far slower, and far more consequential than either of those things. It's called AMOC, the Atlantic Meridional Overturning Circulation. And to understand what it does, you have to first understand something about the ocean. The ocean is not one thing. It is not a single body of water sitting still beneath the atmosphere. It is a system of interconnected circulation patterns, layered by temperature and salinity, constantly in motion. And AMOC is the engine at the center of that system in the Atlantic Basin. Here is how it works. Warm, salty water from the tropics, from the Gulf of Mexico, from the Caribbean, from the equatorial Atlantic, moves northward along the surface of the ocean. This is the current you might know as the Gulf Stream. It carries heat. It is what keeps Western Europe, which sits at the same latitude as Canada, from experiencing Canadian winters. As this warm water travels north, it gradually loses its heat to the atmosphere. It cools, and as it cools, it becomes denser. In the North Atlantic, near Greenland and the Norwegian Sea, this water becomes so cold and so dense that it does something extraordinary. It sinks. It plunges thousands of meters to the ocean floor, and then it flows south again, deep below the surface, all the way back toward the tropics. This is the loop: warm water up, cold water down, south to north on the surface, north to south in depth. A vertical conveyor belt stretching the length of the Atlantic Ocean, driven entirely by differences in temperature and salt concentration. Scientists call this thermohaline circulation. Thermo for heat, haline for salt. It has been operating in one form or another for millions of years. And for the last 12,000 years, the entire span of human civilization has been remarkably stable. The key word there is has been. Before we get to what's happening to AMOC, you need to understand the full scale of what it controls, because most people hear ocean current and think weather, coastlines, maybe some fish migration. The reality is much larger than that. AMOC transports roughly 20 million cubic meters of water per second northward across the Atlantic. To put that in perspective, that is more than 100 times the combined flow of every river on Earth. It is the single largest movement of water on the planet's surface. And because water carries heat, this means AMOC is also transporting an enormous amount of thermal energy, approximately 1.3 petawatts of heat. That is roughly equivalent to the output of 1 million large power plants, continuously transferred from the tropics to the North Atlantic. That heat doesn't stay in the ocean. It releases into the atmosphere. It warms the air over Western Europe, keeping temperatures in the UK, France, Germany, and Scandinavia 5 to 10 degrees Celsius warmer than they would otherwise be. Without AMOC, London sits at the same latitude as southern Labrador in Canada. If it lost AMOC's influence, it would have winters to match, but AMOC's influence extends far beyond Europe. It influences the West African and Indian monsoons, which provide rainfall for billions of people. It regulates sea surface temperatures that determine whether Atlantic hurricane seasons are mild or catastrophic. It affects the positioning of the intertropical convergence zone, a band of rainfall near the equator that governs precipitation across Central America, the Sahel, and parts of Southeast Asia. AMOC also plays a critical role in the ocean's ability to absorb carbon dioxide from the atmosphere, as warm surface water is pulled north and then sinks into the deep ocean. It carries dissolved CO2 with it, locking it away from the atmosphere for centuries. Scientists estimate the ocean absorbs roughly 25 to 30% of all human CO2 emissions annually. A significant portion of that absorption depends on the overturning circulation remaining active. and then there is sea level. The northward flow of AMOC actually suppresses sea levels along the U.S. East Coast. The current creates a slight gradient, a slope in the ocean surface that keeps water elevated in the mid-Atlantic and depressed near the coast. If that current slows, that gradient weakens and water redistributes, the U.S. East Coast from Florida to Maine would see sea level rise above and beyond global average projections. All of this, the European climate, the monsoons, the hurricane seasons, the carbon cycle, the East Coast sea levels, is being maintained right now by a temperature and salinity difference in the North Atlantic, and that difference is being disrupted. The evidence, the first serious warning came in 2004. Scientists using underwater floats and mooring systems, a monitoring network called RAPID, deployed across the Atlantic at 26 degrees north, began systematically measuring the strength of AMOC for the first time in history. What they found when they had enough data to analyze was alarming. Between 2004 and 2012, AMOC had weakened by approximately 15%. That was faster than any climate model had predicted. The initial response from much of the scientific community was cautious. The data set was short. The variability was high. More data was needed. More data came. And in 2018, a landmark paper in Nature used indirect climate proxies, ocean sediment cores, ice cores, coral records, to reconstruct the strength of AMOC going back 1,600 years. The conclusion was clear. AMOC is now at its weakest point in at least a millennium and a half. The slowdown is not a short-term fluctuation. It is a trend. In 2021, a separate analysis published in Nature Climate Change found 5 independent indicators, all pointing to AMOC approaching a critical threshold: sea surface temperature patterns, salinity changes, subsurface ocean heat content. Each one independently showed the same directional signal, and the mechanism driving this is well understood. As global temperatures rise, the Greenland ice sheet melts. Greenland is losing ice at a rate of approximately 280 billion tons per year, a figure that has roughly doubled since the 1990s. This meltwater is cold and fresh. It pours into the North Atlantic at an accelerating rate, and fresh water is less dense than salt water. It floats. This is the problem. AMOC depends on cold, salty North Atlantic water sinking to drive the circulation, but the influx of fresh meltwater is diluting the salinity of the surface ocean. Water that should be sinking is staying near the surface instead. The engine is being starved of the density difference it needs to run. What makes this particularly concerning is the nonlinear nature of the system. AMOC does not weaken smoothly and predictably. It has 2 stable states, on and off. Under the right conditions, it can switch between them relatively rapidly in decades rather than millennia. We know this because it has happened before during the last ice age. AMOC switched off and on multiple times in response to pulses of meltwater entering the North Atlantic. These events, called Dansgaard-Oeschger events, caused temperature swings of 10 to 15 degrees Celsius in Greenland within decades, not centuries. Decades. The last major shutdown occurred approximately 12,800 years ago during an event called the Younger Dryas. A massive pulse of glacial meltwater flooded the North Atlantic. AMOC collapsed, and the Northern Hemisphere was plunged back into near glacial conditions within a few decades. It lasted almost 1,200 years before AMOC restarted. We are, right now, adding fresh water to the North Atlantic at rates that, while slower than a glacial outburst flood, are sustained, accelerating, and show no sign of stopping. What collapse actually looks like. In 2023, a study published in Nature Communications attempted to model not just whether AMOC would collapse, but when the researchers used early warning statistical signals, mathematical fingerprints of a system approaching a tipping point, applied to 150 years of ocean data. Their finding, if current trends continue, AMOC could collapse sometime between 2057 and 2090. The midpoint estimate was 2057. The lead author, Peter Didelson, noted that the speed of collapse, once it began, would surprise even the most pessimistic climate scientists. That study was immediately contested. Other researchers argue the methodology overstated certainty. The IPCC, the Intergovernmental Panel on Climate Change, assessed an AMOC collapse as unlikely this century but acknowledged low confidence in that assessment and recognized it as a high impact, high uncertainty risk. What no serious scientist disputes is this: AMOC is weakening, the direction is clear, the debate is about speed and threshold, not about whether the trend is real. So let's talk about what an AMOC collapse or near collapse would actually produce. Not the gradual warming scenarios you've heard before. What happens to a world where the North Atlantic heat pump stops working? Exists. The U.S. East Coast floods without AMOC's current suppressing sea levels near the American coast. Sea levels from Miami to Boston would rise by an additional 0.5 to 1 meter above global average projections. Cities that had engineered their flood defenses to a certain baseline would find themselves below the new waterline. This is not slow inundation. Storm surges that currently happen once in 100 years would happen. The monsoons fail. AMOC is connected to the Atlantic Intertropical Convergence Zone, the atmospheric boundary that drives rainfall patterns across West Africa, the Amazon, and South Asia. A collapsed AMOC would shift this boundary southward, reducing rainfall across the Sahel by 20 to 30%. The Indian summer monsoon, which provides roughly 70% of India's annual rainfall, would weaken. This is not an abstraction. India has 1.4 billion people. Their food system depends on monsoon rains arriving on schedule. The Amazon dies. The Amazon rainforest is already under stress from deforestation. And warming, it has its own tipping point, driven by the amount of moisture it can recycle internally. A weakened Atlantic monsoon system, combined with continued deforestation, could push the Amazon past its threshold. Models suggest that once 20 to 25% of the Amazon is cleared, we are currently at approximately 17%. The remaining forest begins to dry from the edges inward. A collapsed AMOC would accelerate this process. The carbon cycle breaks. If AMOC stops, the ocean's ability to absorb CO2 from the atmosphere decreases significantly. More CO2 stays in the atmosphere. Temperatures rise faster. Greenland melts faster. More fresh water enters the North Atlantic. The process becomes self-reinforcing. This is what scientists mean when they call AMOC a tipping point. Not just that it tips, but that its tipping triggers other tipping points.
We do not fully understand the role of deep-sea hydrothermal vents in the heat budget of the circulation. We do not know whether there are feedbacks operating at depths we have barely touched that could accelerate or buffer the slowdown. In 2023, researchers mapping the deep Atlantic found previously unknown underwater mountain ranges, seamounts taller than the Alps, that significantly alter the path of the deep return flow. These features had simply not been in the models. They changed the calculated speed of the deep circulation by a measurable amount. The Labrador Sea, one of the two primary sinking regions that drive AMOC, showed an unexpected interruption in deep water formation between 1995 and 1997. The cause was never fully explained. It restarted. But the episode revealed that AMOC can experience regional shutdowns that are not captured by the broader monitoring systems.
There are also questions about the interaction between AMOC and the Southern Ocean, the body of water circling Antarctica, which connects the Atlantic, Pacific, and Indian Oceans through the global thermohaline circulation. Changes in Antarctic sea ice coverage, which has hit record lows in 2023 and 2024, may be altering the density of water entering the Atlantic at depth in ways that current models do not fully. What this means is that our projections for AMOC are already alarming. Our projections based on incomplete information. The system is larger, deeper, and more interconnected than our measurements currently capture. The 2021 paper in Nature, Climate Change, that identified 5 tipping indicators explicitly, acknowledged this. The authors noted that their analysis was limited to the observable surface and near-surface signatures of AMOC. The deep ocean, they wrote, remains substantially under-sampled and under-modeled.
We are watching a change in the largest circulation system on Earth's surface. And we are watching it through a keyhole. Closing. In 2004, the same year the Rapid Monitoring Array first began recording AMOC, a disaster film called The Day After Tomorrow was released in cinemas. In it, AMOC collapses over the course of a few days, triggering instant superstorms and a new ice age that freezes New York City under 100 feet of snow. Scientists spent years pushing back against that film. It's too fast, they said. It's too dramatic. That's not how the climate system works. And they were right. The Day After Tomorrow is not how AMOC collapses. The real process is slower, less cinematic, and in many ways harder to confront, because it unfolds over decades rather than days, which makes it easy to ignore, easy to deprioritize, easy to treat as someone else's problem in some future decade. But here is what is true. The system is weakening. The measurement is not in doubt. The direction is not in doubt. And the consequences, for European winters, for U.S. coastal cities, for the monsoons that feed billions of people, for the Amazon, for the ocean's capacity to buffer our own emissions, are not speculative. They are the outputs of a system we understand well enough to model, even if we do not understand it well enough to be certain. The Younger Dryas, the last time AMOC shut down, took a civilization that had not yet built one to collapse. We are, as a species, entirely more capable now. But we are also more dependent. More people, more infrastructure, more agriculture calibrated to climates that have been stable for centuries, all of them resting on the assumption that the North Atlantic will keep doing what it has always done. That assumption is no longer safe to make. The Atlantic Meridional overturning circulation has been running since before humans existed.